Hello, it's Scott Manley here. Blue Origin was founded more than 20 years ago by Jeff Bezos using the money that he made at Amazon to pursue his space dreams. They have developed 4 generations of engines, starting with pressure-fed hydrogen peroxide and scaling up to staged combustion methalox. These BE-4 engines will of course power their massive New Glenn rocket, which will hopefully launch before the end of the year. But for now, the only spacecraft they've sent to space has been their new Shepard crew capsule. But the only hardware that this space company has sent to space on its own has been suborbital hops on its new Shepard spacecraft, which offers passengers a few minutes of zero gravity and the view of the Earth from on high. Many like to dismiss this as nothing more than a joyride, but for the money, it's the highest you're gonna go. And I love the fact that they've sent some really deserving people like Wally Funk, Ed Dwight, and of course William Shatner, who said this.
Everybody in the world needs to see. There is Mother and Earth and comfort, but what you see is black. What you have given me is the most profound experience I can imagine. I'm so filled with emotion about what just happened. It's extraordinary.
Now, I'm not here to argue that New Shepard is a great rocket and is going to outcompete SpaceX. I am here to answer a question that I get asked all the time. Why does it look like, the shape of rockets is pretty much defined by the laws of physics and the engineering decisions made by the designers. And so how did these forces conspire to create a rocket which resembled a flaming weapon of pleasure? And for those of you who have never heard the male organ described in quite that fashion, this is from John Cleland's Memoirs of a Woman of Pleasure, which was written over 250 years ago and therefore had to lean heavily on metaphors. And during the rest of the video, I will be relying heavily on this source material for other suggestions. So let's start out with the physical characteristics of this stately piece of machinery. The resemblance is uncanny. It is more than a stiff insinuation, and a big part of it is down to how thick it is. It's not so much its absolute diameter, but its ratio of height to girth. If you look at this chart, the Falcon 9 booster on the left has actually the same diameter as the New Shepard on the right. They're both designed to be road transportable, and so they have to be less than 12 feet wide on the back of a truck. That's about 3.65 meters, so 3.7 meters in diameter. The original Falcon 9 was shorter, but when they wanted to expand the fuel tanks to get more performance, they had to stretch the booster because they couldn't make it any wider. And so, despite being so much taller and more powerful, it looks a lot less like an enormous, unmerciful machine than the much shorter New Shepard. And the second big factor is the front of the rocket. The fact that the front has a profile which obviously expands outwards and then curves over in a pleasing shape of an arc. Now again, that capsule is about the same diameter as SpaceX's Dragon capsule, but it doesn't have all the requirements for on-orbit maneuvering, so it's really focused on internal volume for crew. That's why it takes this nice curve, a compromise between the aerodynamics and providing the maximum volume for the minimum mass. So the top of the capsule is curved for aerodynamics on ascent, and then the sides of it are sloped because you want that for stability during the descent. And so inside of this, there is a ceiling above which there's a bunch of gear, primarily the parachutes, 3 drogue parachutes, 3 main parachutes. There's a floor with other gear below it, and extending up into the middle, there is the large solid rocket motor that is used in the abort scenario, or as John Cleland might describe it, a grand movement. This was from October 2012. This was the first powered flight of New Shepard's crew capsule, and I believe that this was actually part of NASA's Commercial Crew Development Project, so they actually got some NASA money to demonstrate this capability. This would also demonstrate the parachutes, which are designed to slow the descent, and the retrothrust system, which is used to soften the landing, and we'll talk more about that later. But because of the NASA involvement, I think this is why we have this publicly available cross-section showing the capsule design at that point, which is a pretty good reference for understanding the design of this. One interesting part of this is that if you look at the nozzle of that central abort thruster, it looks to me like there are control vanes that extend out into it. So I think that is likely how this thing steers during that process. And, I'm not sure whether they actually had this stuff in there for the test, but you can see the size of the crew couches and the racks or the bookcases, because, hey, that's exactly what you want to be doing while flying to space is reading a book, right? Now, the second propulsion system that's on the spacecraft, the one that's actually used in flight, is the reaction control thrusters, and there's a few ports that you can see on this diagram here. I believe these are cold gas and compressed nitrogen, which is used for attitude control on ascent and descent. This is after the capsule has been released from the booster and is flying on its own. Obviously, it has to maintain the correct attitude during ascent. If it flipped upside down when it was falling back, the people inside would fall onto the ceiling, and that would be really bad, and they could get injured very easily. They also use this to put a small rotation on the spacecraft, just for stability, I believe, and also to let the people see a panoramic view of the world below them. It's also possible to spin the capsule at a speed which allows experiments in lunar gravity using centrifugal force. Okay, so the final propulsion system is the one that's used during landing, and this is mentioned during every live stream because it kicks up so much dust, and they don't want people to think that's the capsule exploding as it touches the ground. Now, when it's descending under parachutes, it's coming down at about 17 miles per hour, or about 28 kilometers per hour. That would make for a pretty rough landing, so as it comes down towards the surface, it fires a thruster system that slows the thing down before it actually touches the ground. So according to the physics of drag, basically the rate at which you descend under a parachute is a sort of inverse square relationship with the area. If you want to cut your speed in half, you need 4 times the area of parachutes. So quickly your parachutes are going to get very large and unmanageable. Also, the slower you descend, the more the spacecraft is going to drift as the winds blow it around. And if you're trying to land within a specific area, there's a real incentive to have a high descent rate and then have a thruster system slow you down right at the end. And this is what the Soviet Union did with the Soyuz. As it comes down, there is a sensor system which has a gamma ray emitter, and then there's a receiver, like a Geiger counter, that detects this when it gets close to the ground, and it activates a set of solid rocket motors, which slow it to a stop right at the end. China's Shenzhou copies the Soyuz design, so it has that as well. But if you look over the new Shepard capsule, you don't see any large ports for rockets. There's obviously the one in the middle, which is used for the abort system, and then there's some small attachment sites inside of that ring. But then there's no bigger thruster ports. And this post-recovery image doesn't show any large places where thrusters might have been uncovered during the landing process. What we do have, however, is this series of small holes around the outside, and I believe that those are the landing retropulsion thruster ports. And I believe that these are visible in this cross-section from the NASA paper. It looks like there might be a common manifold that runs all the way around that's fed by gas right at during the landing process. And sometimes if the atmospheric conditions are right, you can see this firing just before the dust cloud. Did you see it there? Let's look a little more carefully. There's no fire or flames, just a hint of condensation in the air as the gas expands and cools. Now, this is almost certainly heavier than having a solid motor retro rocket, but it's probably safer, and I suspect that the ring shape actually causes gases to expand in under the spacecraft and cushion the landing a little bit more than a single thruster would. But maybe some people with actual fluid dynamics skills can do some CFD and confirm my suspicion. The important thing being the capsule is no longer a furious battering ram when it touches down on the ground. One other thing that helps, by the way, is this ring. That is a crush core ring that absorbs any excess force right at the end. This has to be removed and replaced after every flight. It's one of the few parts of the spacecraft which isn't reusable. Now, I want to stop for a little aside. I remember I was talking about this launch abort test back in 2012. Well, back then, they had previously flown New Shepard, but it was somewhat different from the instrument of mischief that we know today. Yes, this was the original New Shepard, built back in 2011 when Blue Origin were working with kerosene and hydrogen peroxide engines. It had 5 pressure-fed engines on this stage, and they were able to successfully demonstrate an ascent and a descent and soft landing using this system. Now, obviously they abandoned this design. It was tested without a capsule on top of it on a number of flights on 2011. And part of these design requirements was to demonstrate that it could go up and then come down safely. And since it landed vertically on rockets, it needed to descend from altitude in that attitude. And that's why they had some innovative aerodynamic features. Now, the most obvious thing is these fins, which they look backwards, don't they, right? Well, these were actually patented as bidirectional aerodynamic fins. So during the descent, they actually build a shockwave in front of it. And if normal fins extended into this shockwave, it could produce very high, unpredictable loads. So they angled them like that to avoid this problem. The other thing they did was they added this drag brake at the top. It was a conical surface which would fold out. And again, they patented this, and I believe they actually were supposed to test this on their new Shepard design. There aren't any photos that I can find showing this hardware actually being built or tested, but on this image of the rocket, you can actually see the structure in the stowed position. And I don't think this is a mock-up, because they lost this vehicle when they were doing a high-speed test. They were flying it at Mach 1.2 when it went out of control and they had to terminate the flight. And if they were flying it that fast, they must have been expecting to bring it back down unpowered using passively stabilized aerodynamics. So they lost this vehicle, and then at some point they abandoned their roadmap, which was to go from this test vehicle to a suborbital vehicle to a large orbital vehicle, all using this conical drag brake at the top. And I think this is because NASA gave them funding to develop the BE-3 hydrogen engine, and so they went from developing a first stage vehicle to developing a testbed for an upper stage engine, the BE-3. And so they stopped working with hydrogen peroxide and started working with liquid hydrogen, no longer the plaything of a boy but the weapon of a man. And the BE-3 engine was a great step forward, a sturdy stallion of an engine. It was a tap-off cycle, hydrogen-oxygen, deep throttling capable engine, which of course is also going to be modified to work on the new Glenn second stage. And so in April 2015, they flew New Shepard for the first time in the form that we recognise. John Cleland may have described it as a naked, stiff, erect, wonderful machine. Blue Origin had demonstrated they were able to tame the beast of liquid hydrogen, and as the spacecraft thrusted majestically skyward, it would ultimately carry the capsule to an altitude of over 300,000 feet. But Blue Origin stopped short of declaring this an absolute success. Their plan had always been to recover the booster from the very first flight onwards. However, according to the press release, there was a problem with the hydraulic system that resulted in the loss of the booster. Now, they didn't go into exactly how this was a problem, but in the days following, an RV-6 pilot went out looking and he found the impact crater. And it wasn't right next to the landing pad, so we can surmise that it wasn't a hydraulic failure of the thrust vectoring as it came into land. This was an aerodynamic failure that was much higher up. And this leads us neatly back to the discussion of its characteristic shape. A big part of its uncanny resemblance to Love's true arrow is the fact that the shaft is narrow, and then as it reaches the head, it expands outwards. And there is a well-defined ridge that goes all around the circumference. And that is a critical aerodynamic device that is designed to allow the rocket to fly aerodynamically stabilized trajectories both forwards and backwards. You see those steering fins on the bottom of the rocket, they make it passively stable when it's going forwards, but if it was to go in reverse, those would make it unstable. So, the space at the top is a ring fin, which is occluded by the capsule during most of the flight, and then when the capsule separates, air is now free to move through it. Of course, there's no air at this altitude. But soon enough it begins to fall down, and that will passively stabilize it by moving the center of pressure up. But in addition, there are these four fins that fold out during the descent, and then as they get deeper into the atmosphere, they deploy these drag brakes. And the drag brakes are essentially there to slow the spacecraft down as it descends through the atmosphere, diving down into Mother Nature's embrace, one might say. If you look carefully at the top of the frame, you can actually see the paint starting to turn brown from the atmospheric heating. Apparently they use a spray-on thermal protection coating, which is, slowly charred over multiple entries into the atmosphere. So anyway, this upper structure is primarily about moving the center of pressure towards the top of the vehicle. The steering is still using those fins that are at the bottom of the vehicle. And as it descends, it will use those fins to guide itself towards the landing pad. and it'll only fire up the engine a few thousand feet above the surface, and then once it gets close to the surface, that's when it actually performs the final terminal navigation and soft landing on the pad. And it is absolutely worth mentioning that Blue Origin were able to refly a booster that had gone to space before SpaceX had managed to do so. But of course, this was on a vastly different scale compared to the grandeur that is the Falcon 9. One notable moment in an early flight was when they performed an abort at max Q, and they actually expected the booster to be destroyed, but the booster actually recovered and landed. And while future missions were flown with a new booster which had a number of improvements to it, the booster that had been recovered, it went on display. In fact, it went to Oshkosh, which is where we get this great photo. I like this image because it shows the booster from above, and you can look down inside that circular fin and see the support structure in there. This booster would also be on display in the lobby of Blue Origin for some time, and it's now being moved to the Smithsonian. Incidentally, the different capsules all get names. The first capsule built was the RSS Jules Verne, and that was used on the first two boosters and performed the abort test. Second capsule was the RSS H.G. Wells, and it performed most of the science experiments. It also achieved the maximum altitude, where they fired the launch escape system right at booster separation, carrying it up to an altitude of 119 kilometers. And it would be the capsule carrying those science experiments on NS-23 on September 12, 2022, when they had an engine failure, which resulted in a real-life abort of the spacecraft. So booster number 3 would be lost, but the capsule, the H.G. Wells, it of course, the escape system performed correctly, it landed, it returned to Earth, and when New Shepard returned to flight, it would be booster 4 carrying H.G. Wells. Booster 4 is the one that has been carrying all the human flights, and its capsule is the RSS First Step. And so this is the program's standout instrument of pleasure. And with the arrival of Booster 5, we got the RSS Karman line, which I find interesting because they didn't get quite as far across the Karman line as most of the other spacecraft. Anyway, returning to our original question, there is one other factor that I want to mention, and that is that the shaft is not perfectly smooth. There are, the technical name is raceways, but they carry plumbing, they carry wiring, the essential lifeblood of communication up and down this vehicle. As such, it's not unreasonable to think of these as arteries or veins running along the length of its shaft. So here's one example showing the raceway coming in from the left and reaching to the top of the vehicle here. And you can see some wiring and pneumatic tubing going through there. Also, this angle shows that there is a space on top above the fuel tank where hardware can sit in the front of the vehicle. These raceways get fat towards the bottom because that's where the landing legs are stowed. And yeah, this image shows the rear section of the booster before the tank has been attached or before the engine goes in. These are the legs that have been partially deployed. When these get fully deployed, those gold struts, they extend all the way in and they latch at the base. These are all from recruiting videos that Blue Origin put up on their page showing the cool people that work there, how great it is to work at Blue Origin. This image, I believe this shows the tank of the New Shepard, and judging by the length of it, it looks like the hydrogen and oxygen tank must be using a common dome design. Again, this is not something that I've seen them mention specifically, but it makes sense from the hardware I've seen. But most people aren't nerds like me, they're just looking at the entire package, fully assembled, and when it stands up, it truly is an object of terror and delight that will pierce the heavens. And while many people find the idea of suborbital spaceflight on New Shepard to be something that they would love to do, something they would spend money on, not everyone agrees. We live in a world where political forces are seeking to divide us for their own gain. But these passengers looking down on the Earth from above realize that we are but one species, and we, viewers, looking at this rocket, realize that it does in fact look like, And to quote John Cleland once again, an amazing, pleasing object of all wishes, all dreams, all love, the King member indeed. Huge respect to all the engineers at Blue Origin that worked on this and made it the way it is. I'm Scott Manley. Fly safe.